last time we had our first examples of, well, unknotted surfaces for space, and these were given by, and I don't think I gave them a name, but we'll call them FG, just because we let FG be the boundary of the genus G handled by the HG, and this is living inside S3, which we think of as living in S4, and this was the unknotted genus G is unknotted or unknotted non-orientable surface. Okay, so let's consider the Mobius band. M, and I guess let's call this guy M plus in S3. So what does this look like? The non-compact. The compact one. Hang on. This. This is the crossing, right? This is M plus. And the reason I call it M plus is because this crossing here is a positive half twist of the band. Okay. All right, so since the boundary of M plus is the unknot in S3, we can cap it off, or we could say this, there's a disk. D in S3 with boundary of D equal to U. Okay. So we also have sort of this is our U, this is our U, same U. And we get some disk D here. This will be M. Okay. Now, of course, there's no way to move this disk to this Mobius band in the 3-sphere and have the result be embedded. So, so D cannot be made, I should say, or I could say like this, made disjoint from the interior of M plus inside S3. Okay. So why is that? Why is it that we don't know why we can't embed a non-orientable closed surface in free space? I don't know. Proof the answer. I mean,
Or has a non-removable self-intersection.
oh yeah, but that's true. Does that tell you that you can't glue on the disk and have it be embedded?
Intersection.
Can't accept, but you cannot do that with the client boxes, right?
Yeah, same thing with the Klein bottle.
You can still take the cord when Mobius bands. It's in the client bottle.
But a neighborhood of that core is embedded. Yeah, so, well, one way to do this is to use homology, Alexander duality, together with the universal coefficients. So I think this is an exercise in Hatcher. And the contradiction you get is that if a closed surface, maybe it's more general, closed surface embeds in S3, then H1 of the surface is torsion free. So, I mean, essentially, it's probably just making rigorous your intuition. So anyway, if you feel like having a refresher on algebraic topology, that might be a fun thing to think about. Okay, so that's why non-oriented. So when we created these orientable surface knots, we sort of started by just sticking them in S3 and then considering them as a cross section at S4. So we can't do that if we want to come up with non-orientable examples because they don't fit in S3. Okay, but if we just perturb the interior of D into the four ball, one of the four balls bounded by this S3, we get a surface which I'll note P plus, which is M plus union D inside S4 embedded. So then we surely have no intersections between, the only intersection between the disk and the Mobius band then is the unknotted boundary, because the Mobius band lives entirely in the 3-sphere. So maybe sort of, I have an action schematics like this. So here we have S3, and then below S3 is a 4-ball. We also have a 4-ball above S3, right, giving us our S, of course, here. That's the idea here is sort of this thing going on. And up here we've got, wow, great, switch colors. And then the disk comes down. So the disk is properly embedded in the 4-ball. Meaning it intersects the 4-ball in its boundary. Okay, and so by doing this, we get a embedded projective plane inside 4 space. Okay. So we can also let P minus be the other projective plane formed in this way. Right, so start with the Mobius band with the other twist. Okay. All right, and so maybe I'll just say that yeah, let's say like this. The surface knot S in S4 with S homeomorphic to a projective plane is unknotted if and only if S is isotopic to 1 of P plus or minus. So this is kind of a cheap way to define what it means for a non-orientable surface to be unknotted. You just construct the simplest example you can think of, and you claim that it's unknotted. But of course, you know, RP2 doesn't bound a 3 manifold, so there's no natural analog to defining it unknotted in the way that an unknotted orientable 3 manifold, or the unknotted knot in S3, the one that bounds the disk. So we can't quite do that. All right.
That's good exercise too. P2s and not 3 manifold.
I didn't prepare that one. Is that a hatcher exercise also?
I can't remember.
You can't remember.
I got it.
Fine. All right, more complicated things. Okay. Let S and S prime, let S equal the disjoint union S1 and S2. Okay. sorry, not disjoint union, split union. Of two surface elements. In this setting, for dimensional knots and links, it meant that the free ball in the free sphere that contained one of them would be a better way to say it than saying that they're separated by a sphere. Okay. I should have defined it. Well, anyway. Figure out those two things. Okay, let omega be an embedded arc with boundary of omega. Yeah, how do I write this? So we want the boundary to intersect each of these things non-empty, and we want the interior of omega to intersect these things non-empty. Okay, so arc connecting these two surfaces. Okay, so let's maybe start drawing an example here. So we've got some piece of surfaces. We've got this S1, 2, and then we've got this arc omega. I don't know why I drew it with a curve. There it is. Okay. Let's let N be a three-dimensional neighborhood of omega, such that N intersect S sub I, this piece of I is as a disk. Okay, so what does that mean? We've got a disk D1, we've got a disk D2, and we've got this solid 2 neighborhood of omega. And so what we're going to do is we're going to surge your omega, which means we're going to remove a neighborhood of the endpoints and replace it with the boundary of the two. So let's write that down. So let's let S prime equal, take S, which is the union of these two things, remove the disks from each piece of it, and then glue on the boundary of N plus the. So what is S prime going to look like? S prime is going to look like this. Okay, we've just attached a tube between the surfaces using the arc omega. We call S prime connect the zone of S1 and S2, and we write S prime equals S1 connect zone. Yes. Okay, and then the exercise is to show S prime doesn't depend on the arc omega. So I could have picked that here. So this is very similar to an exercise we did semester, in the semester when we showed the connected sum of knots was well defined. All right, any questions about that?
By restricting your cumulative to be three-dimensional, I guess that's why you don't have to worry about the framing then, doesn't it?
Yeah, exactly. Yeah, and one way to think of it is actually that the arc omega could be, well, it could be isotopes to lie in like in an S3 cross section of S4. In which case you would have a tubular neighborhood inside that S3. You can just take that one. So this operation, I've drawn this in dimension 3. And I claim that actually locally you can make this lie in a 3-ball say and do everything as I've just drawn. So that would be like the good thing to roll into this exercise to check. That's a good question. Okay, and so yeah, again, I defined connected sum for knots. If you have links, then you have this problem of it depends on which components you choose to connect them along and stuff like that. I guess one thing that I didn't plan to say anything about, but I guess we could mention at this point is itself. And so you have some sort of surface knot, you could find a properly embedded arc and run it from that surface knot to itself, and then you could search it. And this will increase the genus of the surface knot, give you a new surface knot. That's not bad. I wouldn't call that anything like the connected sum, but that is an interesting operation. For example, if you have a knot sphere, I guess understanding good if you search her along there. Okay. So maybe I'll bring that up later at some point. Does that make sense? That's something that didn't really happen for 1-knots. You couldn't connect some of 1-knot. So.
And also like thinking about fluid too. It's interesting.
Also thinking about what side you go to. Sorry, I was also distracted by what I said about 1-knots. I guess it can. It is we actually sort of did talk about this for 1-knots because and here, okay, so this gets to your framing question also. I see. So here, if we took an arc, then what you can do is you take a codimension 1 regular neighborhood, which ended up being a band, and you could attach a band to a knot with both endpoints. Let's see. Okay, so this is sort of the analog. Yeah, exactly. This is the analog of attaching a band to knots, except we don't need to worry about the framing in this case, except for maybe the inside or the side of the surface you touch it along. Does that matter?
When you
When you do it to yourself. Oh yeah, because it can get an orientation reversing handle attachment. Right. Okay. Okay, so I think I either straightened that issue out or made it more confusing. Not sure which, but all right. So let's let P sub ij equal the surface obtained by taking I copies of P plus, connect summing them together, and then connect summing that to J copies of P minus. Okay. And what we see is that Pij is homomorphic to Xij copies of RP2. And we define these to be unknotted non-orientable surfaces. So a non-orientable surface knot is unknotted if it is isotopic to Pij for some I and j. I guess you need to have at least one of these. Okay. And then I guess I could say a non-orientable surface link is unlinked if it is isotopic to the split union of P I J's. IJs. Okay, cool. What we see is that note that there are I plus j distinct unknotted surfaces. Yeah. I got the complexity wrong. I wrote differently in my notes. I think I wrote that there are G plus 1 distinct as homeomorphic to the connexome G copies of RP2. Okay, and I mean, there's a strong claim here, which is that these things can be distinguished. And that's not something that I think we're prepared to do right now, but the basic idea is that these are distinguished by their regular neighborhoods. In S4. Okay, so a regular neighborhood of a surface in a 4-manifold is going to be a disk bundle over that surface. And so you can calculate the Euler number of that disk bundle. And that's an invariant of those disk bundles that will distinguish these. The Euler number of these will be, it will be 2i minus 2